The first stage of the manufacture of nitric acid is illustrated by the following chemical reaction. We put equal masses of both of them in and we're asked to determine the limiting reagent. So the first thing that we need to do is we need to work out how many moles of each do we have. Number of moles is equal to mass over molar mass. So for the ammonia, I'm going to take 750 grams and I'm going to divide it by 14 plus 1 plus 1 plus 1, which is 17, and I land up with 44,12 moles. Simultaneously, I have got 750 grams of oxygen, and the oxygen 32, because it's O2, 16 plus 16, and I land up with 23,44 moles. Now we're going to do a little ratio. If I have ammonia and oxygen, they are in a 4:5 ratio. And therefore, if I have 44,12 of ammonia, I would require 55,15 of the oxygen. That's not possible. So the next thing that we're going to do is we're going to say, what about if I did it the other way? NH3 to O2 is 4:5. I have got 23,44, and over here I have got 18,75 because I divided by 5 and I multiplied by 4, and therefore this does work. So this is my limiting reagent. And I would then obviously land up with some leftover ammonia because of the 44,12. The next question is, what mass of NO should be produced? So if I've now decided that this is my limiting situation, we decide on using that number of moles of oxygen because that is my limiting reagent. So what am I going to do? I'm going to say, we need to keep the balanced equation, so let's maybe make that. So I'm going to go and I'm going to say oxygen is to NO as 5:4, and we're then going to say 23,44 is to 18,75. We just did that earlier but for a different situation, but it comes out the same. And then mass is equal to number of moles times molar mass, which is equal to 18,75 multiplied by the 30. Where did I get 30? 14 plus 16 over here, and I land up with 562,56 grams. If the actual yield during the investigation was 491, what is the percentage yield? So you're going to say, well, I got 491,2 out of a possible, I should have got 562,56, and therefore times that by 100 and my percentage yield comes out to be 87.32%. There's a missing slide here. I'm not quite sure where it's disappeared to, but basically we landed up with 20 tons of a certain substance, and so we have to get number of moles is equal to, and it all seems to work out quite nicely when you go 20 tons is actually 20 million grams, and the substance that we had, the total, it was ammonium nitrate. Yes, the ammonium nitrate broke up. We first had to balance the equation, so it was 2 NH4s, NO2 gives me 2 N2s plus 4 H2Os plus O2. And then the molar mass of ammonium nitrate is 80. So my number of moles turns out to be 250,000 moles. They then asked you, what is the total volume of gas? So I'm going to say NH4, NO2 to gas is going to be 2 is to 247. And therefore I'm going to take the 250,000 and I'm going to make it into divide by 2 times by 7, and I get 875,123, and then I'm going to say volume is equal to number of moles times molar volume, which is going to be 875,000 multiplied by 22,4, and I land up with 19,600,000 decimeters cubed. I've got this titration, and I'm expected to label the apparatus or the observations. You've got to brush up on this. This is a retort stand. This thing was a burette. Over here is the tap of the burette. This thing is called a conical flask. And over here we have the meniscus. In a neutralization experiment to determine the concentration of nitric acid, given a standard solution of sodium carbonate was used. To prepare the sodium carbonate, you use the following, and it's dissolved in 100 centimeters cubed of water. 20 centimeters cubed is neutralized. So let's see what they actually want. Firstly, it's a definition, and a strong base is a substance which readily accepts protons. Calculate the concentration of the standard nitric acid solution. So the first thing is number of moles is equal to mass over molar mass. So it's 0,53 divided by 106. That is equal to 0,005 moles. And then my concentration is equal to number of moles divided by volume. People are getting this wrong when it's on the information sheet. Really not acceptable at this point. You've got to get at least the formula right. And now I've got the concentration of the sodium carbonate, so I am in a position to try and work out my titration. Number of moles of acid over number of moles of base is equal to concentration of acid, volume of acid, concentration of base, volume of base. It's equal to 1:1, except for the fact that this isn't balanced. So we need to go 2 over there, 2 over there, and then it's going to work. So it's going to be a 2 of acid, 1 of base, and I then land up with concentration of acid. The volume of acid is 33. The concentration of the base I've just worked out. The volume of the base is given to me over there, and I therefore land up with 0,06 moles per cubic decimeter. Use the information given in the following table to determine the indicator which is most suitable. Well, you've landed up with a strong acid and a weak base, so you're going to now say that you're going to have an acidic endpoint, and your acidic endpoint will land up being there. So methyl orange is the best one. Why? Because nitric acid is a strong acid, and at least sodium carbonate is a weak base, so they will have an acidic endpoint. The next one is we're given ethanoic acid is a common organic acid. The dissociation constant for this acid is given. Write an equation for the ionization of ethanoic acid in water. So it's CH3COOH. You know that from organic chemistry. Put it into water, and we're going to have one proton donor. So it's going to become CH3COO minus plus H3O plus. So that's the dissociation in water. Write an equation, what is the significance of a low Ka value? That tells me that it is a weak acid. What does it indicate about the electrical conductivity? Well, it means I'll have very few of these ions, and therefore few ions means poor electrical conductivity. Will an aqueous solution of salt, sodium ethanoate, be acidic or basic? Sodium comes from sodium hydroxide, which is a strong base, and the ethanoate is from a weak acid called ethanoic acid, which we've just discussed, and therefore it's going to land up being a basic end point overall, and give a reason for your answer. Because sodium hydroxide is a strong base, ethanoic acid is a weak acid, and therefore you will land up with a basic salt. Now we've got this mass of a burning candle. It gets monitored. This information is given to us quite clearly. Asks you to draw a graph of the data on the back page. It's actually very simple. It's literally time and mass of candle. You put them in and you land up with a cute straight line graph. Don't just try and isolate an area. Please put your zeros into your physics graphs. They need to all be there. So we needed a heading, we needed axes labeled, we needed consistent scales, and we needed our points. Calculate the average rate of consumption. The rate of consumption is change in Y over change in X. So it's going to be change in Y over change in X, which is 23,4 minus 24,5. I happened to choose those 2 points. You could have chosen other points along the way. 24 minus 12. 24 minus 12, and I mean I could have got those points off the graph as well, but I didn't, and I get negative 0,09 grams per min. I did not make a big deal about the negative, but actually you need to show that it's decreasing by 0,09 grams per minute. Now the next thing is calculate the rate of carbon dioxide production in moles per minute for that same time period. So what you're going to do is you're going to say C28H58 is to carbon dioxide as 2 is to 56. Now, I know I was losing at that rate, so instead of 2, I am going to land up with number of moles is mass over molar mass, which is equal to 0,09, divided by the molar mass of carbon dioxide, which is going to be, sorry, not of carbon dioxide, of this ginormous candle wax formula, and it turns out to be 394, and I get 2,2 times 10 to the negative 4 moles. Put it in here, 2,2 times 10 to the negative 4, divide by 2 times by 56, 0,006 moles, and therefore I am producing 0,006 moles of carbon dioxide every minute. Examine the following mechanism. Identify the catalyst. Catalyst has to be the same at the beginning and the end. So I get rid of all of that. What's the same at the beginning? In the first steps reactants, and in the last steps products, the water. So why could you identify that? Because it was the same at the beginning and at the end, present at the start and at the end. The Maxwell-Boltzmann distribution curve shows an uncatalyzed reaction. On the diagram, indicate the change that would occur if a catalyst were introduced. This tells me the amount of energy, and this is normally how much energy you require to react. What does a catalyst do? It reduces the amount of energy to react, and so a catalyst would just bring down the activation energy and change that number there. Study the chemical reaction below to identify 2 ways, other than the use of a catalyst, to increase the rate of this reaction. So I have to increase the surface area of the zinc by chopping it into a powder. I have to increase the concentration of the hydrochloric acid, and I could say generally that I need to increase the temperature. But you need to be specific with these. You can't just say increase surface area, increase concentration, increase temp. Well, you can just say increase temperature, but you can't say the other two. And then finally, it says draw a sketch energy profile to represent the reaction. Well, we know that it's an exothermic reaction. Label the energy of reactants, the energy of products, the activation energy, the heat of the reaction, and ensure that your axes are correctly labeled. The x-axis is called course of reaction, and this is potential energy. You need to show the shape of a exothermic reaction as well in that, and this is pure bookwork. It's a level 1 question, and really you should be getting full marks for it.